Good afternoon, everyone. I'm Anwesha Patel from Indian Institute of Technology, Bhubaneswar, under the Decentralized and Smart System Research Group, and I'm going to present my work on the topic Efficient Coordination in Internet of Things through Fast Many-to-Many Conveyance of Bulk Data. These are my content. Talking about conveyance of bulk data or multimedia data, it is one of the most important requirements in advanced applications of IoT. In scenarios where infrastructure is good, the conveyance of bulk data is also good amongst the devices. However, conveyance of bulk data in many locations like mining, forest, volcanoes, which have a weak connectivity and involve a significant communication of bulk data such as images, acoustic data, the weaker connectivity makes it difficult for conveyance of bulk data here. Also, in possible disaster situations like flood, earthquake, which needs immediate response and communication, it can pose a problem in such situation as there are dynamic changes and have almost weak or absent connectivity. And in these emergency situations, conveyance of bulk data becomes even more critical. Also, conveyance of bulk data is needed in modern day applications like the intelligent transportation system, which can help serving various purposes like detecting congestion, helping dynamic computation of path, and also maintaining safety and security. In our work, we are focused on developing IoT assisted lightweight intelligent transportation system. In many of the existing works of IoT, they often use cloud services, which makes but these cloud services are highly centralized and the latency increases. It also bears multiple problems related to single point failure, making it very vulnerable. Also, in cases where they are not resilient against dynamic changes in the installation, since the connectivity can be weak in some of the unforeseen circumstances or in disaster situation like the flood, earthquake, using cloud can be detrimental. Therefore, in this work, we take an endeavor to develop lightweight solution to serve advanced needs of ITS in a self-sufficient fashion. Edge devices in the intelligent transportation system can collect and analyze, and if we make these edges intelligent, they can make decisions themselves. Uh, they can make the decisions themselves also more resilient to dynamic changes. Efficient conveyance of data thereby increases, building a self-sufficient autonomous process. However, IoT devices bear several constraints based on their power, computing capabilities, memory, and energy budget. Although these IoT devices are sufficient for sharing low dimensional sensor data, they will not perform well for sharing multimedia data, which is heavier in size. Therefore, an efficient and effective communication between these IoT devices are very important. For communication of data or for data transmission, broadly, there are two strategies of communication as present: asynchronous mode of communication and synchronous mode of communication. In asynchronous communication, they normally use the CSMA CA, where packet collision mostly occurs due to multiple transmission of packets at the same time. And because there are multiple transmission at the same time, there is a rise in communication traffic, thereby causing significant loss for time and energy. Whereas in synchronous communication, it is time synchronized, making it help avoid collision, thereby increasing the bandwidth utilization. It uses the physical layer phenomena like the capture effect and constructive inferences. Therefore, in our work, we consider the synchronous communication for data transmission. Talking about the literature survey, it is evident that IoT has played an active role in several works of intelligent transportation system. Sophisticated algorithms like the greedy Bayes, DB scan, kernel density algorithms are used, but all these algorithms are resource intensive, computationally very expensive, and most work is done through the GPS or already available map, which is accessible through the Google Cloud. However, our emphasis in this situation where connectivity is low is like rural areas, underwater, forest, volcano sites, and mainly disaster situation where cloud support or accessing Google Maps or GPS won't be available. Therefore, our main objective includes to design many-to-many conveyance of bulk data, which is done using a strategy called chain bus to infer road network through communication-assisted coordination with the roadside units. And thirdly, to build a road network, we need to re-identify vehicles passing through the roadside units, for which we have used an intelligent lightweight vehicle re-identification strategy. Talking about existing strategies where the normally the entire data is chopped into a set of packets, and then each of this packet is disseminated independently using one to many flooding from one source, and this is sequentially repeated from each of the source node, making it many to many sharing. However, this sending of data one by one, that is until the completion of transmission of the previous data packet is done, in this existing strategy, the next data packet is kept on hold, and this sequential repetition actually causes a lot of wastage of time and energy due to recurring overhead for doing network coverage. Instead, our proposed strategy named chain flood, we exploit the concept of pipelining, and we have assigned pipeline based one to many dissemination strategy, as we can see here, and this is done using time triggered architecture of synchronous transmission. So this actually reduces the sequentially repetition from each of the sources, and it reduces latency to a very big extent. Now this chain flood is extended to the chain bus, that is many to many conveyance of bulk data, that is from all the nodes. Chain flood is being done, and in this and chain bus, it schedules the instances of the chain flood from each of the source roadside unit using their corresponding IDs, and this actually is the many to many conveyance of bulk data. For example, as we can see here in N2 and N6, there are a set of images that is being captured by these roadside units of about the devices. The images, both these roadside units have detected new vehicles and have captured their images. And a basic step of pre-processing is followed, and lightweight intelligent re-identification of vehicle is being done, for which they require a little more time. Here, to transmit any bulk data received, we have also incorporated the dynamically extended slot, as we can see. So they pre-process and compress the image and use chain flood to transmit in slot 2 and slot 6 of the chain bus, and in this way chain bus and chain flood operates. After one complete round of chain bus, the roadside units now obtain the compressed images captured by the other roadside units in the entire network. Later, the roadside units tries to match these images of vehicles that is most recently seen with other images via inter roadside unit communication network. In this, there is a build graph module which executes independently in each of the RSUs to construct the road connectivity structure using a simple bit matrix which sets if a vehicle is being captured by the RSU. And to build the connectivity between the roadside units, we now need to re-identify the vehicles if they are same or different. For this, instead of any complex algorithm, we have used a simple, intelligent, lightweight vehicle identification strategy called structural similarity index, which is based on shape, structure, and basic characteristic of the vehicle. And this constitutes the bulk data about the vehicle. And this information is captured and this is being transmitted. And for this to transmit this, as we have explained already, this is dynamically done in the chain bus. Talking about the results, we will be discussing the performance of our proposed model along with the structural similarity index. In this, firstly, the performance of the proposed model, we have used two metrics, that is the reliability and the latency. As we can see, reliability of both the existing model and our proposed model are almost same. However, our model, that is the chain bus model, has less latency and actually performs 54.3% faster compared to the previous modules. So this proves that our model is better than the existing strategy. Talking about the performance of the structural similarity index, structural similarity index is studied under the effect of threshold of similarity, wherein the highest accuracy and precision, which is above 90%, is achieved if we have adjusted our similarity threshold around 80%. Next, we have discussed about the road connectivity network through the inter-RSU coordination, and NV here is the number of vehicles introduced in the system, which influences the convergence speed. The graph evolves way faster with more vehicles and more rounds of iteration. This concludes that our strategy of integrating chain flood with intelligent lightweight vehicle re-identification strategy, called the structural similarity index, is resource efficient and performs way better than existing strategies. Finally, talking about the future work, in future we plan on developing lightweight IoT based solution in focus to difficult areas where connectivity is particularly weak, like the rural areas, forest areas, mining areas, etc., and in possible disaster situation like the flood, earthquake, etc. So I would like to conclude my presentation over here, thanking you for all of your patient listening.